Hi everyone. In this video I want to talk about one of the most famous concepts in quantum mechanics, which is the uncertainty principle. We've been talking a lot about how the heart of quantum mechanics is the wave-particle duality. Particles are waves and waves are particles, and we want to talk about how that is encoded in this thing called the uncertainty principle. So what I'm going to do is I'm going to largely introduce to you conceptually some ideas related to the uncertainty principle, how it shows up in various ways as a reflection of the wave-particle duality, and then I'll also write out the equation for the uncertainty principle and explain what it means. The idea is that particles act both as particles and waves, but the uncertainty principle tells you that you can't see the wave and the particle nature at the same time. So here you can see a photo with a long exposure. This photo shows some motion. So you get a sense by looking at this photo that the people in the photo are moving in a certain direction and with a certain speed. On the other hand, they're kind of blurred out. We don't know exactly where the person is. We have some idea, but it's not perfect. On the other hand, if you're doing a photo finish at a race, for example, like shown here, you want the very short exposure. So this photo was taken with a very short exposure. You can see exactly where the people are, but you don't really have any sense of how fast they're moving. There's no blur associated with them. This is the same kind of idea that is encoded in the uncertainty principle. So the equation for the uncertainty principle is like this. Sigma x, sigma p, is larger than or equal to h bar over 2. So h bar is, of course, Planck's constant. So in this equation, sigma x is the uncertainty in the position, and sigma p is the uncertainty in the particle's momentum. The product of those two is always larger than or equal to h bar over 2, which is a small number. But the idea is I can never know either one of these exactly, because if I knew the position exactly, then the uncertainty in the position would be 0, and this would be violated. So in quantum mechanics, this whole thing is always obeyed. You cannot violate Heisenberg's uncertainty principle. I can't know the position or the momentum exactly, and if I know the position really well, then I won't know the momentum very well in order to satisfy this inequality. What does it mean to know the position well or the momentum well? What do I mean by the uncertainty in the position or the uncertainty in the momentum? Suppose you have a particle which is described by some wave function. I'm just going to make up some wave function. Let's say something like this. So this is going to be x. This is going to be the wave function psi of x. And better yet, rather than just one particle, imagine you have thousands of particles. You have an ensemble of particles described by this wave function. So you want to imagine a bunch of particles. So you imagine a bunch of identical systems. All have the same wave function, for example. And then suppose you measure the position of each of these particles. Okay, so this is, remember, this is a probability distribution. In quantum mechanics, the wave function, when I square it, is going to be the probability distribution. And so this particle would be more likely to be found here, and also likely to be found here, and very unlikely to be found at the origin or here. Right? But if I measure the position of the particle, it's going to be found somewhere, just more likely here and less likely here. Now imagine I do that for all of these thousands of systems, all described by this same wave function. I can average those measurements. So I can determine the average x is found by averaging all of those position measurements on all of the identical systems. And of course you can measure x squared, which is the average squared position. And what do I mean by the uncertainty in the position? The uncertainty in the position is the standard deviation, x squared minus x squared. Okay. So if the wave function is very localized around a certain range of x, then I'm going to know the position pretty well, and my standard deviation will be small. And I could do the same thing with the momentum. I could take all of these particles, which are all described by the same wave function, individual systems, a whole bunch of them identical, and I could measure the momentum of each one and average all of those. That would tell me the average momentum. and I could do the same thing, measure the square of the momentum, so that's the average momentum squared. And the uncertainty in the momentum is the standard deviation of those measurements. So when people say the uncertainty of the position and the uncertainty in the momentum, what we're talking about is that if you made identical measurements of an ensemble of systems, how spread out are those measurements, or how clustered together are those measurements? What's the standard deviation in the x measurements? What's the standard deviation in the p measurements? We can go a little bit further to understand this by thinking about the de Broglie wavelength. We learned that particles act like waves, and the wavelength of a particle is h over p. So it's inversely proportional to the momentum. H is just a constant, right? So think about what this means. If I know the momentum very well, I also know the wavelength very well. So a well-defined momentum is similar to a well-defined wavelength. Another way of saying this is if you know the position really well, I don't know the wavelength of the particle very well. And if I know the wavelength of the particle really well, I don't know the position very well. There's where you're seeing the wave-particle duality. X is like position, something which has a well-defined position is like a particle. Something which has a well-defined wavelength, which is related to momentum, is like a wave. As an example, consider a particle which has a wave function drawn in the figure there. If someone asked you, what's the position of this particle, you'd probably say, I don't really know what you mean. It's sort of spread out all over the place. It doesn't really have a well-defined position. But if someone asked you what the wavelength was, you could easily figure that out, right? This function repeats pretty regularly. I could measure the distance that it takes for it to repeat. I could figure out the wavelength pretty well. So this is an example of a quantum system which has a poorly defined position. So sigma x is large. The uncertainty in the position is large here, but the wavelength is pretty well known. Sigma p is small. So I would say this is sort of a wave-like behavior, a wave-like system. Let's contrast that with something like this. What if this was your wave function, and someone said, what's the position of the particle? You would say, oh, it's pretty obvious. It's right where the peak is. So the particle is almost always going to be found around x equals 7. So the position is well defined. Sigma x is small. The uncertainty in the position is small. But if someone asks you, what's the wavelength of this particle? You would be like, what do you mean? It doesn't really repeat. How could I assign a wavelength to it? So sigma p is large. The uncertainty in the wavelength is very large. And so this is more particle-like. We had two examples of wave functions there. One is acting more like a wave, one is acting more like a particle. Finally, let me come back to the famous double slit experiment. So I'm going to send electrons through here, one at a time, and they're going to show up on the screen. There's two openings here. And when you have both slits open, you find that there is going to be an interference pattern shown on the screen. So what I'm illustrating here is where is it going to be brighter on the screen and where is it going to be dimmer. There's going to be something like this. So areas of bright spots and dark spots. So what's going on here is I have a wave-like behavior. So this is wave-like. I'm seeing the interference here. But what happens if I cover up one of these? So let's say I block this. So I now allow the electron to only go through one. If I block one of the slits, so I don't allow the electrons to pass through this slit anymore, what will show up on the screen will be something more like this. I won't see the interference anymore. So this is more particle-like. How do I understand this in terms of the uncertainty principle? If I force the electron to go through this slit, I'm localizing it in this area. So I'm making sigma x is small. It has to go through here. Sigma x is small. If sigma x is small, that means sigma p will be big, which means I lose the wave-like behavior. It becomes more particle-like. If I open this, now the electron can pass through both slits. Sigma x becomes larger, sigma p will be smaller, and I get the wave behavior back. So that's another reflection of the uncertainty principle. Sigma x, sigma p is larger than or equal to h bar over 2. If I localize the electron, I force it into a small area, sigma p will get large and I will lose the wave-like behavior. So in this video, I introduced you to the uncertainty principle. We talked about these uncertainty and position and momentum are really standard deviations of a bunch of measurements of identical systems. And we did some conceptual work to understand this equation. The fact that something that has a well-defined momentum also has a well-defined wavelength. It's more wave-like behavior. Something that has a well-defined position is more particle-like. It's localized like a particle is. I hope you found these conceptual examples useful, and we will pick it up here in class. Thank you all for listening.